Okay, so we're going to do a bit more mathematical induction, and this time we're going to look at two different ways of handling the inductive term. So when we get to k plus 1. So please don't make this the first mathematical induction video you've ever watched. This is for somebody who's been doing it for a little while. So as you can see, we've got an example here. We're required to prove 1 plus 4 plus 10 plus so on up to n terms equals n outside of 3n minus 1 over 2. First thing we need to do is the general term, or the nth term. Now, this one might be a little bit different to some of the ones you've seen. It doesn't have an expression to summarize the nth term. So how do we go from one term to the next using n as a member or an element of the expression? If we look at the jump and how we would use that, if we go 3 times the term number and then take 2 off, that will work. So let's have a look at that. So for the first term, which is 1, if we go 3 times 1 because it's the first term, and then minus 2, it's 3 minus 2 and we get 1. For the second term, which is 4, so it's 3 times the second term minus 2, that's 6 minus 2 is 4. Third term, 3 by 3 is 9, minus 2 is 7, so that works. So we rewrite that. 1 plus 4 plus 7 plus 10 plus ... plus 3n minus 2. Okay, so that's more useful. So we do need that general term, the nth term. Sorry, I didn't mean for my braces to be hanging below the vinculum line there. Okay, so, well, we do what we normally do. The base case, and we let n equals 1, and let's look at the left hand side. Well, that's just the first term, so that one, and left hand side equals 1. Right hand side now. So the right hand side is we substitute 1 in there, so we got 1, 3 by 1 is 3. Oh, hold on, that's better. I just had to write the correct number in there. So it's a 1. So 1 outside of 3 by 1, which is 3 minus 1 is 2 over 2. Again, that's 1. So it's true for the base case. So hold, good spelling, holds for the base case. Okay, that's always pretty easy. And the hypothesis now, so we generate our inductive hypothesis and the resulting equation, the expression left and right. So because we're going to use that again, I've just highlighted that in yellow. And now this is where the two methods, they're subtly different, but this is where they diverge. Okay, so I'm going to show a method there, then later I'm going to show the alternative there. But they're related. So on the left hand side is the first method, and so I'm going to work on the left hand side of the column you see below. I'm going to, using basically substitution, generate the inductive step now. So inductive step where we make n equal k plus 1, generating just what that would look like. So we have 1 plus 4 plus 7 plus 10, whoops, and so on. Like last time, we had the 3k minus 2, and subbing in k plus 1, so we have 3 times k plus 3, take 2, which is plus 1. And that equals, through substitution again, so on the, just looking at the yellow term, imagine putting in k plus 1 wherever you see k, essentially, k plus 1, and then we have 3k plus 3, take away 1 is 3k plus 2 I just couldn't quite fit it between the columns there. It's a 3k plus 2 over 2. Now what we have is here we see that sum equals that sum there. And of course it equals the yellow zone on the right, so we can replace what I've underlined here with the yellow highlighted part, which you see starting to appear below there, plus the inductive term, which is 3k plus 1. I've labelled that left hand side. We're going to develop that now, and when we're adding fractions we need to put them over the same denominator. So we have k, this one's already over 2 on the left hand side, k outside of 3k minus 1, and this one would need to be multiplied by 2 over 2. Okay, so 2 over 2, which is essentially 1, which doesn't change the overall value of it, but we would have, for it to be over 2, we'd have to have 6k plus 2 there. Developing that further, expanding and simplifying, we have 3k squared minus k plus 6k plus 2 all over 2. Then we have quadratic on the numerator, 3k squared plus 5k plus 2. We can factorise that quadratic into 3k plus 2, k plus 1. And that's over 2. This is great news because we can see that here and here are the same thing. So that equals the right hand side. So you would write your statement as I've shown in previous videos, since yada 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 true for n equals 1 and when yada yada yada. You should be writing this out fully, of course, but just that I've done it in so many other videos. When n equals k, it's also true for n equals k plus 1. By induction, it's true. Okay, that was a bit informal, the end of that, but I haven't finished yet. The other part we've got to reconcile is when we go back to this step here and we do something different, because last time I used substitution straight up. This time, if we add the inductive term to both sides, so the arrow there is when n equals k, the inductive hypothesis step. So if we've got that, and then here's an alternative for you. See how you feel about this. So we've got that same sum there. Now this is where we add on the inductive step to both sides. So that comes out as 3k plus 1 as we saw last time. Now it is axiomatic that if we do, what did we just do to the left side there? We added 3k plus 1. It's axiomatic that if we add the same to this side, the right hand side, they remain equal. Okay, so I need to keep a bit more line discipline, don't I? I'm going up the hill a bit there. I'm sorry about that. So putting that in and then adding that inductive term on. So it's a different line of thinking, right? But it's still fine. It's axiomatic. It's all consistent, and I've just added the same thing to both sides. That same thing is the inductive term. Now I'm going to develop the right hand side. That makes it different to the other approach. So the right hand side is kind of like the algebra we did down here, okay, in that zone over there. Thus I'll go a bit quicker then, and you can see what's forming is that same quadratic situation as before. (3k plus 2, k plus 1). Can you see it there last time? That was it there. So 3k plus 2, k plus 1. That's a good sign. Now, we haven't done what we need to do here. We haven't shown that it works also for the substitution. So what we write now is, but for n equals k plus 1, we can substitute it in to here. Okay, so following that same pattern. So it's like the opposite, thinking in the opposite direction to the first way. So the yellow inductive hypothesis term for the right hand side, we can substitute k plus 1 into that. So let's do that. So it's k outside of 3k minus 1 over 2. So we have k, which is k plus 1, outside of 3, outside of k plus 1, minus 1, oops, over 2, and k plus 1, and we have 3k plus 2 over 2, simplifying that, alright, which equals right hand side. So then you write your concluding statement as we did last time. So two different approaches you can reconcile together.